Today we shall learn about the interactions of particles and photons with matter. Let's look at the objectives for today. After today's lecture, students will know about charged particles, neutral particles, and photon interactions with matter. Students will be able to define specific ionization and linear energy transfer. Students will know about which interactions are directly ionizing and which are indirectly ionizing. We shall also learn about the attenuation of photons and the influence of various interactions on image contrast in diagnostic imaging and mammography imaging. Finally, we shall learn about the K absorption edge, half value layer, and beam quality for photons. Let's start with charged particle interactions. Energetic charged particles interact with matter through Coulomb forces and lose their kinetic energy by excitation, ionization, and radiative losses. Let's start with excitation. Excitation occurs when energy is transferred to an orbital electron, causing it to jump to a higher energy orbit. The atom is in an excited state. After a short time, the excited electron returns to its original energy level with emission of electromagnetic radiation or an Auger electron. This is called de-excitation. The next type of particle interaction is ionization. There are two types of ionization interactions. Charged particles like alpha particles, betas, protons, and any nuclei may cause direct ionization. Uncharged particles like photons and neutrons cause indirect ionizations. This table summarizes the types of interactions we can expect. Let's look more closely at ionization. Ionization occurs if the energy of the incident electron exceeds the binding energy of an atomic electron it interacts with. The atomic electron is removed via charged particle interactions, leaving a positive ion and a free electron. The free electron may produce secondary ionizations, leading to production of delta rays. Direct ionization is caused by charged particles like electrons and heavy ions like protons, alpha particles, and deuterions. The bottom part of this figure shows the process of ionization, with the incident electron knocking an outer orbital electron out and the emission of a secondary electron or delta ray. The threshold for ionization is when the energy of the incident particle is at least 10 electron volts. Some places use the threshold of 13.6 electron volts, which is the binding energy of the electron in a hydrogen atom. After ionization, an ion pair is formed, consisting of the ejected electron and the positively charged ion. Ion pair energy is the average energy required for a charged particle to produce an ion pair in air. Ion pair energy is denoted by the letter W, where W is equal to 33.85 electron volts per ion pair. The ion pair energy W includes energy expended in overcoming electrons binding energy, excitation, and interaction with other atoms, as well as the kinetic energy of the ejected electron. The average energy required for a charged particle to produce an ion pair in soft tissue is 22 electron volts per ion pair. Specific ionization is defined as the average number of primary and secondary ion pairs produced per unit length of the charged particle's path. It is expressed in ion pairs per millimeter. Specific ionization is proportional to squared charge and inversely proportional to the squared incident particle velocity. So a heavy charged particle like helium having two positive charges will have a higher specific ionization compared to an electron having a single negative charge. Also, for a given charge, slower particles will have higher specific ionization. As a charged particle moves through a medium like air, it slows down, so its specific ionization increases to a peak called the Bragg peak, as shown in this figure. Linear energy transfer is a measure of the average amount of energy deposited locally in an absorber per unit path length. It is a description of local energy deposition in a medium and has an impact on absorbed dose to tissues. Linear energy transfer is equal to specific ionization multiplied by the W energy, which is the energy needed to form an ion pair in air. For example, if the specific ionization is 4 times 10 to the power 6 ion pairs per meter and W is 33.85 electron volts per ion pair, then LET can be found by multiplying 4 times 10 to the power 6 ion pairs per meter by 33.85 electron volts per ion pair. This gives us an LET of 1.35 times 10 to the power 5 keV per meter. LET can also be expressed as the squared charge divided by a particle's kinetic energy E subscript k, as shown by this formula. One way to differentiate between heavy charged particles and light charged particles is to observe their ionization paths in matter. Heavy charged particles like alphas make short, dense, straight line tracks in matter, while light charged particles like electrons follow a more scattered, less dense ionization path in matter, as this figure shows. The path length of a particle is defined as the distance the particle travels. Light charged particles like electrons cover longer path lengths or distances than heavy charged particles. This is seen in the figure shown. The alpha particle path and range are equal, while the electron path is longer than its range. Heavy charged particles like alphas also deposit more energy over a short range than light charged particles like electrons. The range of a charged particle is the straight line distance it travels before coming to a complete stop. Range is equal to particle energy E divided by LET. This formula is applicable to heavy, highly ionizing particles that travel in a straight line while losing kinetic energy. We can use this for alpha particles as an example. If E is equal to 4 MeV for an alpha particle with an LET equals 1.35 times 10 to the power 5 keV per meter, then range is equal to 4 divided by 1.35 times 10 to the power 5 keV per meter. So range is equal to 0.03 meters or 3 centimeters in air. Light charged particles like positrons have a short range in tissue. When the positron reaches its range, it can interact by annihilating an electron. This results in conversion of rest masses of the two particles, the positron and the electron, into two collinear photons. This is used in PET imaging. The next kind of charged particle interaction is by radiative losses. These are losses due to deceleration of the charged particle as it interacts with the nucleus. This results in Bremsstrahlung radiation, which we call X-rays. We shall learn more about this on the lecture on X-ray production. This figure shows a charged particle producing Bremsstrahlung radiation as it interacts with the nucleus. In this interaction, the charged particle approaches the nucleus and is attracted by the positive charges in the nucleus. So if it's moving fast enough, it can keep traveling. If it's moving slowly, it eventually will crash into the nucleus. But during this interaction with the nucleus, it emits Bremsstrahlung radiation as its path is deflected. There is a relationship between radiative energy losses due to Bremsstrahlung and ionization energy losses. It is expressed as the ratio of radiative energy loss to energy loss by excitation or ionization and depends on the atomic number Z of the target material and energy E subscript K of the incident particle. This formula is used in the selection of target materials for X-ray production. It means high atomic number targets are better at X-ray production than low atomic number targets. The table shows the efficiency of X-ray production at different energies for a given target material. During X-ray production, the incident electron energy is proportional to the tube potential in kilovolts. At higher tube potentials, the efficiency increases. At 4000 kV, efficiency of X-ray production from a given target is 40%. In the diagnostic energy range of between 50 to 150 kV, X-ray production is less than 1% efficient. This table shows 1% efficiency at 200 kV. During X-ray production, most of the electron's energy goes to heating up the target material. Let's look now at indirectly ionizing radiation. Indirectly ionizing radiation is what we get from neutral particles and photons. Neutrons are neutral particles so cannot directly interact by Coulomb forces. They interact primarily through billiard ball collisions with the nucleus of light elements in tissues. Light elements like hydrogen, carbon, and oxygen. As these nuclei recoil, they lose energy via excitations or ionizations. In tissues, neutrons interact with hydrogen in water, producing recoil protons or recoil hydrogen nuclei. These recoil protons lose energy via excitations and ionizations. We shall look at the interaction of photons like X-rays and gamma rays next. There are four main types of X-ray photon interactions with matter. Three of these are important in diagnostic imaging and nuclear medicine. The first is Rayleigh or classical scattering. This type of interaction is not important in diagnostic imaging or nuclear medicine because it has a low probability of occurrence even at mammography energies. The other types of interactions are Compton scattering and photoelectric absorption, which is used in diagnostic imaging, and pair production, which is the basis of positron emission tomography imaging in nuclear medicine. Let's start by looking at Rayleigh scattering next. Rayleigh scattering is also called classical scattering and involves the excitation of the total atom. There is no ionization. After Rayleigh scattering, there is essentially no difference in energy between the incident and scattered photon. This type of scattering occurs infrequently in diagnostic imaging. It is less than 5% of all interactions at say 70 keV. At about 30 keV, as in mammography, only 10% of interactions are Rayleigh scattering. The next X-ray photon interaction is Compton scattering. The probability of Compton scattering is almost independent of atomic number Z, but varies linearly with electron density. It is the predominant interaction in soft tissues at energies above 100 keV, as seen in this graph. It also decreases with photon energy, as the graph shows. The right figure shows what happens at atomic level. The photon knocks out an electron that is loosely bound from the outer shell. The ejected electron and photon are scattered at different angles. The photon has less energy and so a longer wavelength, as this figure shows. When high energy photons interact with low Z materials like soft tissue, Compton scattering dominates. The radiographs shown here are of a rat pelvis at different photon energies. This is to illustrate the effect of Compton scattering at different photon energies. At 70 keV, there is less Compton scattering, but at 1.25 MeV, there is a lot of scattering, so the radiograph contains more noise. The most probable interaction in diagnostic energy range of between 50 to 150 keV is Compton scattering. The next photon interaction is photoelectric absorption. The probability of photoelectric absorption varies directly as the cube of atomic number and inversely as the cube of energy. In the bottom figure, the absorption edges correspond to K-shell binding energies. At the absorption edges, the photoelectric absorption increases sharply when the photon energy is equal to the binding energy of the electron shell. Photoelectric absorption is the primary contribution to contrast in diagnostic radiology. Photoelectric absorption dominates when lower energy photons interact with high atomic number materials. It is used to amplify differences like the differential absorption between tissue and contrast materials. For example, the K edge of iodine and barium are at 33.2 keV and 37.4 keV. These energies are close to the effective energy of most diagnostic X-ray beams, so there is strong absorption of the photon by iodine and barium in this diagnostic range. This increased differential absorption of iodine and barium at diagnostic energies relative to surrounding soft tissues and bone contributes to increased contrast in diagnostic imaging. This figure shows the photoelectric effect at diagnostic energies for tissue, bone, and sodium iodide. So you have tissue, bone, and sodium iodide, and you can see the difference here is what creates the differential absorption, which leads to increased contrast in diagnostic imaging. The last interaction we shall look at is pair production. In pair production, the photon interacts with the nucleus, where the photon energy is converted into an electron and a positron pair. Both electron and positron lose their energy by excitation and ionization and come to rest after a short distance. When the positron comes to rest, it interacts with an electron in an annihilation reaction to produce a pair of collinear photons of 0.511 MeV radiation. This is a threshold process that will not occur if the photon energy is below 1.02 MeV. Let's now learn about attenuation of photons in matter. We saw a few slides back that X-ray photons interact with matter by classical or Rayleigh scattering, photoelectric absorption, Compton scattering, and pair production. These interactions are collectively called attenuation. In the diagnostic energy range, both Rayleigh scattering and pair production are not common, so we can say attenuation is a combination of just photoelectric absorption and Compton scattering. In diagnostic imaging, we use X-ray photons to form an image on a detector. These X-rays are produced with a wide energy spectrum with the maximum energy equal to the maximum potential difference on the X-ray tube. These X-rays are called polyenergetic X-rays. A monoenergetic X-ray is an X-ray beam with a single energy. A polyenergetic X-ray beam can be made monoenergetic by successive filtrations of the beam with attenuating material like aluminum. Characteristic X-rays are examples of monoenergetic X-rays. The X-ray beam used in diagnostic imaging is a polyenergetic beam having a range of energies from a low energy end to a maximum energy as shown in this top figure. When a piece of metal like aluminum is placed in the X-ray beam, the beam is filtered. Filtration hardens the X-ray beam by attenuating the lower energy photons. So the peak of the spectrum shifts to higher energies as shown in the filtered beam in this top figure. The beam intensity is also reduced. The bottom figure shows how different amounts of filtration affect the beam spectrum and intensity. More filtration reduces intensity and shifts the peak of the spectrum to higher energies. Notice that the characteristic spectrum is unaffected by the aluminum filtration. The extent of attenuation of an X-ray beam depends on the linear attenuation coefficient of the material or filter the beam travels through. Linear attenuation coefficient is the fraction of photons removed from a monoenergetic X-ray beam per unit thickness of a material. For a narrow monoenergetic beam, the number of photons transmitted I through a thin slab of material is given by I naught e raised to the power negative mu times x, where mu is the linear attenuation coefficient with a unit of 1 per centimeter, I naught is the number of incident photons, and x is the thickness of the medium in centimeters. When an X-ray beam travels through a material or filter, if the beam intensity is reduced to half its original value, the amount of filtration material in the beam is called the half value layer. So we can define the half value layer as the thickness of material that attenuates half of the incident beam. The half value layer is also a measure of the quality of the X-ray beam and depends on the energy of the X-ray beam, the attenuating material, and geometry. This table gives the half value layer of tissue and lead at different energies. In the diagnostic range, the half value layer of tissue is about 40 millimeters or 4 centimeters. As an X-ray beam travels through some filter material, the beam becomes hardened. Beam hardening is a shift of the peak of the X-ray spectrum to the higher energy end of the spectrum due to attenuation. Hardening is due to removal of the low energy photons from a polyenergetic X-ray spectrum. These low energy X-ray photons increase patient dose without adding to image quality. The manufacturers of X-ray tubes used in diagnostic imaging are required to include added filtration to remove low energy X-rays from the beam. This figure illustrates how low energy photons are removed by layers of filtration. As the beam goes through different layers, the longer wavelengths are attenuated and the shortest wavelength, which has higher energy, remains. When a beam is filtered with a material like aluminum, we can describe the effective energy of the beam. Effective energy is an estimate of the penetrating value of an X-ray polyenergetic beam. It is about 1/3 to 1/2 the maximal value of the tube potential. It can be thought of as the energy of a monoenergetic beam that will have the same effective penetrability as the polyenergetic beam. This table shows the effective energy of different polyenergetic X-ray beams and the corresponding half value layers. As an X-ray photon travels through a material, the average distance it travels before interaction can be calculated from the linear attenuation coefficient or the half value layer of the photon beam. This is called the mean free path. The mean free path is given by 1.44 multiplied by the half value layer. Different energy photon beams will have different half value layers, with higher energies having higher half value layers. So the mean free path will increase with the energy of the photon beam as the half value layer increases with energy. The half value layer of a diagnostic X-ray beam in soft tissue is between 3.7 and 4.4 centimeters for 70 to 140 keV photons. So we can use a half value layer of soft tissue of about 4 centimeters or 40 millimeters. So the mean free path of a diagnostic X-ray beam in soft tissue is 1.44 multiplied by a half value layer of 40 millimeters, and this gives a mean free path of 57.6 millimeters in soft tissue. Let's finish up with a few questions. First question. In diagnostic imaging, what is the effect on image contrast if kV is increased from 70 to 250? The options are no change in contrast, contrast is increased, contrast is reduced. The second part of this question, what is the most probable interaction occurring? Options are pair production, Compton scattering, photoelectric effect, classical scattering. For the first part of this question, what is the effect on image contrast if kV is increased from 70 to 250? The correct choice is contrast is reduced. For the second part of the question, what is the most probable interaction occurring? The correct choice is Compton scattering. Second question. Suppose a photon of energy 1.1 MeV is next to a nucleus. What type of interaction will occur? The choices are pair production, Compton scattering, photoelectric effect, classical scattering. The second part of the question, in what modality is this interaction utilized? First option, mammography. Second, positron emission tomography. Third, computed tomography. And fourth, radiographic imaging. Here are the correct answers to question 2. In question 2, suppose a photon of energy 1.1 MeV is next to a nucleus. What type of interaction will occur? The correct choice is pair production. In the second part of this question, in what modality is this interaction utilized? The correct choice is positron emission tomography. Third question, based on your knowledge of the LET of charged particles, which of these will be most damaging in soft tissue? Your choices are X-rays, beta particles, positrons, alpha particles. The correct answer is alpha particles. Fourth question, above the diagnostic energy range, and in parentheses we have greater than 70 keV. Less than 5% of X-ray interactions can be attributed to what? And the choices are Compton scattering, Rayleigh scattering, photoelectric absorption, pair production. The correct choice is Rayleigh scattering. This is the end of the presentation. Thank you for watching.